everyone. Hi again. Thank you for joining us for this first GECO webinar. This is going to be like the first of a series of webinars we are planning in the framework of the Geothermal Emission Control project, the GECO project. And this is basically an initiative from the consortium to share the knowledge. And we'll be having guests from the consortium, from the partners of GECO, basically sharing their expertise on different topics that we are tackling. GECO is a highly multidisciplinary project, and we are counting on this to be a way to actually give back and share what we have been up to, and also topics that the community can be interested in. So with no further ado, I will share basically with you the program of today. Let's see. So, okay, there we go. Yeah, so so today's topic would be around the Exergy, Exergo-Economic and Exergo-Environmental analysis, also known as 3E, and their methodology, basically an application on geothermal power plants. The program would be as follows. So we will start with an introduction of the GECO project. It will be given by Bergur Sigfusson, who is the project coordinator of GECO, but also a CarbFix member in Iceland. And yes, and after that, we will be diving into the first session around the methodology. We will be having an introduction on the Exergy analysis of energy conversion given by Giampaolo Manfrida from University of Florence. Then we will follow up with the Exergo-Economic analysis by Daniele Fiaschi, also from University of Florence, and then into the other aspect of the Exergy, which is the Exergo-Environmental analysis. And there, Claudio Giuffi would give us an insight on that. We will end the first session by a Q&A session, and then we will take a break of 10 minutes. Then we will go and dive into the second session, and there we will talk about the application of these methods into the GECO project. So Lorenzo Talluri, also from University of Florence, will give us a perspective around the different demo sites and how we apply this methodology in assessing the geothermal power plants that we have in the GECO project. We will end by a Q&A session. So with no further ado, I will give the floor to Bergur to basically give us an introduction on the GECO project.
Let me see. Welcome, everyone. I'm going to expand my screen again. Yes. Okay, I'm just going to go give you a very, very quick introduction of the project and what we are trying to achieve and where we are working and so on. So essentially, the main ambition of the project is to lower emissions from geothermal power plants by capturing them with the aim of either storing the emissions underground in the geothermal reservoirs or to reuse these emissions. We want to basically increase the competitiveness of geothermal, and we don't want to, so by reducing the environmental impact, we want to do this with minimum cost increase of the capital expenditure of the projects. And we also want to develop methods that are energy and resource, let's say, lean. So they are not demanding too much on the output of the power output, for example, of the power plants. We are looking into options and methods to turn the captured emissions into commercial products, and in particular, purifying the emissions so we can indeed produce, for example, pure CO2 And this would generate an additional income or new income stream for the geothermal industry, which is of course a subject that has been under study for a long time, but we are taking it, we are doing one step in that. We want to make our solutions available to both the power and also heavy industries towards lowering their emissions. And what we are also looking at, because we are essentially we are working on carbon capture and storage, and that has been looked at in some geological conditions, and they have a set conditions that have been defined for that, sealed cap rocks and so on. But geothermal is usually not the same as where you would apply conventional CCS. So we are demonstrating how alternative CCS methods can be used in reservoirs that have not been considered before as suitable for CCS or carbon dioxide storage. It's a quite big project. We are 18 partners, and 4 of them are large industrial partners. We have 1 small medium enterprise, and then 13 research and development facilities and universities and so on. We are aiming to do demonstrations in 4 countries, and we have 5 geothermal systems and 1 very low temperature system. In Iceland, nowadays, we have 3 systems, the Hellisheiði and Nesjavellir high temperature power plants, and we have a smaller system in Hveragerði, which is a site that was taken into the project at a later stage, where we are going to test few methods. We are also we have been doing feasibility analysis in Castelnuovo in Italy, which is a high temperature site. And also we are preparing injections in Kızıldere in Turkey, which is one of the large power plants there. And finally, we are looking into options and injecting CO2 into a cold sandstone reservoir in Germany. You can see here it's a quite diverse group of members, and we are scattered around Europe. So just to give you a little bit about the project timeline and what we are investigating. So we started this project in late 2018. So we are just starting the 4th and final year of the project, and the overall concept of the timeline is that we spent the first, let's say, 2 years in the preparation to collect all the information that we need about the sites, define the reservoirs, define the infrastructure that was in place. When we had that when we had collected that, we started the design and engineering of all our demonstration systems both for the capture, purification, and injection systems. And then we are slowly now starting up our commissioning our systems. And here you have some list of what we are doing. We have, of course, been doing reservoir engineering of all the different reservoirs. We are looking into testing new types of tracers to trace the fluids that we inject into the ground. We are optimizing CO2 and H2S capture from geothermal power plants. We have been looking into different purification technologies to deliver pure CO2 to customers. We are looking into new and automated corrosion monitoring methods for the fluids, especially for the fluids that we are injecting into the ground, so we can optimize the casing and the piping infrastructure of the geothermal plants. We are also looking into novel techniques of monitoring the sulfur, where we are injecting it into the ground with laser technology. So essentially trying to, let's say, automate many of the monitoring technologies to decrease the demand by workers and then in turn decreasing the risk posed to workers in working in often quite, let's say, hazardous environments. we are looking into many different variations of injecting gases and water into the ground and into the reservoir. And then we are also aiming to test testing units which will enable zero emission of production wells when they are being tested, and then essentially extracting all the fluid into a testing unit and re-injecting it again without posing any environmental damage. So this is just the, let's say, the general overview of the project, but you will find out more details of what is going on as the talks will be presented during this webinar.
Thank you very much, Bergur, for this insightful introduction. So we will now dive into the first session. And before that, I would just like to remind everyone, especially the guests, that the Q&A session will be taken, all the questions will be taken through the chat box. So please use that. And if you have any issue, just also send it there, and we will take those later. So yeah, thank you. I will give the floor now to Giampaolo and Manfrida to start with the Exergy analysis introduction.
Okay, thank you, Amel, and hello everybody. Thank you, Bergur, for the introduction. I hope you can see my screen, and I will give this first part on Exergy analysis, but this is the whole schedule, which is just the one which was shown by Amel before. And this is something which is connected to the last part of the GECO project, which means the evaluation of the environmental and economic issues of the project. We have been working on the project before on more technical issues. So I will start on what is Exergy. This is the accepted definition. We can read it just that. Exergy, an indicator of the capacity of a system, of a matter stream flow, or of an energy interaction, which can be heat, work, potential or kinetic energy, to produce work when interacting with the reference environment. And there is an equivalence between work and Exergy, and to convert heat into Exergy, you need to apply a Carnot factor, which is defined in this way through the average temperature of the heat interaction. But most of the work we do, especially at system level, we do using physical Exergy in terms of specific Exergy, kilojoule per kilograms, which can be calculated from enthalpy and entropy through the also definition of a reference environment, whose definition in terms of thermomechanical equilibrium is here below. And besides of that, we can calculate Exergy streams in terms of rates of energy, kilowatts, as the product of a mass flow rate by this specific Exergy. And of course, we can also treat reactive processes, but we have done that also in GECO, considering also saline solutions and presence of gases, but today we will not speak about that. The important thing about introducing Exergy is that there is an Exergy balance. We can separate inputs which are positive in this advanced approach to thermodynamics. So everything with a positive mark is entering either as work or heat or as Exergy. And here we have the outputs, which can be useful work, useful heat. Also, we can treat heat, combined heat and power, which is quite common in geothermal applications, but we can also have material streams, so products exiting from the system. And the difference between what comes out of the system and what comes in the system is the sum of all Exergy, destruction and losses. We are treating both destruction and loss. I will make clear what is the difference, but please consider that the balance is essentially non-conservative. Energy is conserved, Exergy is not conserved. Actually, there is an Exergy destruction, and it's treated as Exergy destruction, and there are Exergy losses. It is important that we can you can see that we can define an Exergy efficiency. Of course, it is the output, which are the minus terms, work, heat, or Exergy, divided by the positive terms, that is what you spend to obtain this effect. But the most interesting section is to maintain the denominator always as the input terms and consider an indirect approach to the Exergy efficiency, which you can consider accumulating all Exergy destruction and losses from all the components. And so here it is good to make clear what is the difference. Exergy destruction is connected to entropy generation, that is irreversible processes which are taking place in system components. They can interact also with the environment, internal or external irreversibilities, but anyway, it's a destruction. While an Exergy loss is a direct waste of energy, of Exergy, which means discharge of a stream of matter to the environment or of heat, for example, to the environment. This is a typical example, and we will see what it means in energy systems. And this is a very simple example which shows a graphical representation, which is quite interesting. This is a very simple steam power plant, but it is interesting to see that all Exergy destructions are represented by rectangles which have a height T of the environment, and the base of the rectangle is the entropy generation in the irreversibility, while all Exergy losses are actually treated by somewhat which is on the upper side of the reference temperature. So it's always rectangles, but either it is a condenser loss as this red line, or it is the boiler heat loss because the boiler is not perfectly insulated. Anyway, losses lie over the environment temperature, while all destructions lie below. So from the graphical point of view, it's quite easy to make the difference. To proceed further and to build a bridge to Exergo-Economic and Exergo-Environmental, it is necessary to define the productive structure of the system. And this means representing the system, the topology of the system, have a set of components and streams which should be connected. And within this, you also will define for each component a fuel and the product. The fuel is something you spend to make the component working, and the product is the useful effect of the component in principle. Of course, there are also non-productive components which are quite well outlined by the Spanish school, which is in Zaragoza. Of course, it was originated in Chirche, and they are very important because they guarantee operation of the plant. There are components which do not have a useful output, for example, condensers or cooling towers or steps, which and also the reinjection loss, for example, in geothermal energy is a typical case of something which is non-productive, but it is essential to have the system working. And here there is a general example of a component. The component is a box where a fuel gets in, a product gets out, but there are also destruction. There is a destruction and there is a loss. So the balance overall is that the fuel, what enters, is the product plus the loss plus the destruction. And you can define the Exergy efficiency, but generally when you speak of the Exergy efficiency of the component, you consider only the destruction and you do not consider the loss. While at system level, you include also the loss, because the loss is a system effect. And here there is an example of the heat exchanger. The product is the variation of Exergy from stream 2 to 1, that is heating the cold stream, and what you spend is the variation of Exergy in the stream which is providing the heat to be recovered. And in the case of the turbine, which is a typical example, of course, the useful product is work, while the fuel you spend is the difference between the Exergy entering the system. Here we have 3 inputs and what gets out of the turbine. And of course, the link, you can also have links to the overall Exergy efficiency and the component Exergy efficiency and so on. What means topology? These are references from original papers about Exergy analysis, and you see the definition for each device of what is the fuel, what is the product, what is the device. So there are numbers for the device. And it is also important to understand that there can be loops in energy systems, like in electronic systems. A typical loop, for example, here there is a gas turbine, and the typical loop is that the work for moving the compressor is provided by the turbine at the same cost as the cost of electricity which is generated. And at the beginning, you do not know what is the cost of the work for driving the compressor. So there is, from the topological point of view, there is this type of loop which is feeding back the work produced by the turbine to the compressor input. But this is a teaching example I take from the course I give. If you have regenerative solutions, this is a steam power plant with preheaters. There are 4 preheaters, and of course there are 4 nested loops. So indeed the system can be complicated. But anyway, I'm coming back to the first system, which is a good example. The system can be represented by a matrix. The matrix is putting components as rows and streams as columns, and it has in some way a kind of diagonal approach. When you have +1 means an input, so you see, for example, that the turbine here has an input from streams. The only input is stream 9 here, and it has 2 outputs. Of course, there is a stream 10, which is what is exiting, but there is also stream 18, which is here, which is the work produced. So at the end, you have a linear system, and you can apply typical techniques for solving the linear system. There are several fields of application of Exergy: design level, off-design levels, plant management levels, maintenance level. It can be used for optimization. Here you see a complex system with 7 extractions. It's a steam power plant we analyzed in 2010 with Daniele Fiaschi, and we applied neural networks to repeat the analysis and to determine what was the correct pressure to make the extractions, for example. It's a typical applications. In the case of fundamentals of geothermal power plants, here you have a comparison we did also, I think, in 2010, of single flash and double flash. You have here a pie representation of the Exergy balance, and you can see that indeed the double flash power plant is having a much higher Exergy efficiency, 0.47 instead of 0.38. And indeed, this happens because you mainly reduce the main loss, the main destruction, which was the flash Exergy destruction. This is quite typical by geothermal plants. And if you have a double flash, the sum of the 2 flashes is much lower than what you have in a single flash approach. Of course, you can optimize the pressure of the separator with these processes, so you can use that also for optimization. I will come to the conclusions. There are also something beyond geothermal, can be hybridization of geothermal. We have done simulations of geothermal solar, and we are still doing geothermal plus solar, even at 2 levels of pressure. As you see here, it's a scheme for integrating a binary cycle with 2 levels of pressures. This is the Exergy balance represented here. Most of the destruction is taking place in this solar section here, because the solar collectors are very irreversible indeed, both the high temperature and the low temperature loop. And another possibility which is interesting in geothermal is the combined production of power and cold, because remember that the Exergy can consider outputs as well as electricity, heat, and also cold. In this case, we were doing a study for Torre Alfina, which is a typical location, low, medium temperature in Italy with liquid resource, and we were considering an ORC cycle followed by an absorption power cycle. And you can decide what is better to go to more electricity or more cold production. And this is the end of my presentation, because I will now give the floor to Daniele, if I manage to stop the, yes, I'm managing, okay, to stop my presentation. Daniele, it's up to you.
Okay. Good afternoon, everybody. Can you see my screen, full screen?
Yes, we can see it, Daniele.
Okay. Thank you, Giampaolo. Thank you to the organizers of this interesting event. Now, on the basis of the presentation on Exergy analysis given by Professor Manfrida, I will show you how, with introducing economic and environmental impact parameters, Exergo-Economic and Exergo-Environmental analysis applied to energy system, including geothermal, comes out. So, what's Exergo-Economic? Exergo-Economic analysis combines Exergy and economic analysis to determine the process of cost build-up along the transformation of energy and its depreciation, described by the progressive decrease of Exergy value. This information is very useful, allowing the assessment of the most relevant stages of the energy processes, paving the way to economic system improvement and optimization. The system is defined by its boundary. I'm trying to get the pen. No, sorry. Pen. Here it is. Not. My pen is not working. Sorry. But anyhow, we have in-out Exergy flows, flow rates, heat and work, and delivers useful energy product, generally heat and power. New flows introduced by Exergo-Economic analysis over Exergy analysis are the costs of necessary components to exist, for the system to exist, like capital cost, capital investment cost, and operation and maintenance cost, O&M costs, in order to maintain the system in acceptable good efficiency. The overall Exergo-Economic balance has the units of a flow of money per unit time, euro per second, for example, while the specific costs of Exergy flows are referred to the Exergy unit, here euro per kilojoule, and I am speaking about C coefficients, C parameters, not coefficients. So, at component level, as explained in the previous presentation given by Professor Manfrida, Exergo-Economic analysis required the definition of the function of the component. It implies the definition of fuels and products for each productive component, and eventual auxiliary equations are necessary in case of multiple outputs. Generally, a component can present an Exergy destruction and an Exergy loss, as previously pointed out. An important performance indicator is the relative cost increase across the component, R key, which is the relative increase of product cost across the component key. Reminding the component Exergy efficiency, epsilon k, which was already pointed out by Professor Manfrida in previous presentation, we can put R key in relationship with efficiency and capital cost Zk, while deriving the Exergo-Economic factor Fk, which is useful to assess how much the capital cost is relevant with respect to the cost of Exergy destruction and losses. This is, by the way, the typical behavior of investment cost per unit of product Exergy, vs Exergy destruction per unit of product Exergy as well. Clearly, more efficient components are more expensive, and a relevant improvement of the technology implies, in this example, a shift from green to the red curve. Generally, the components should have this behavior, but there may be exceptions, but I'm not going here to give info about this exception. The scope of the cost model for a conventional geothermal power plant is shown on the left-hand picture, highlighting the maximum disaggregation of components, which allows detailed allocation of cost build-up and addressing the most influencing one. A fundamental step of Exergo-Economic analysis is the definition of component cost correlation, which put in relationship their costs with the relevant working parameters, for example, surface area for heat exchanger or power for mechanical components, and so on. On the right-hand side, the flowchart of cost model generation is shown in this schematic. I apologize, but I cannot use pointers here. I don't know why. Generally, cost data are correlated to relevant operational parameters based on the equipment and process. Here, we propose the example of modeling by IHS Markit Castor that we applied in a recent publication from our group, and the cost correlation function has a logarithmic and a non-linear part. X is a dependent variable which can vary based on the equipment, and C is the cost of the component. Several cost correlation forms may be evaluated to find the best compatibility with the available data. An example of some statistical parameters of cost for some relevant geothermal power plant components are shown in the table below. Here, a couple of examples is referred to a compressor and to an air-cooled condenser. We can see the good correlation of the proposed Castor model, the blue line, with a relevant reference, the Tarton reference for the component compressor on left-hand side picture, while much lower agreement was found for the air-cooled condenser, the right-hand picture. This is an example applied to a relevant case study for GECO that will be described better by Lorenzo. While I move to the introduction of Exergo-Environmental analysis, a parallel approach to thermoeconomics is the Exergo-Environmental analysis, which combines the environmental impact costs in place of economic costs to Exergy analysis of energy systems. Again, three fundamental steps may be identified in the methodology build-up process: the Exergy analysis, the LCA, life cycle assessment, which allows the evaluation of the environmental health impact scores of components and streams of an energy system. Claudio will give you more insights about this in his presentation. And then, third step is the Exergo-Environmental analysis, assigning the environmental impacts to Exergy streams and components, points of impact, generally known as points of impact, and calculates the Exergo-Environmental KPIs, key performance indicators, and performs the Exergo-Environmental evaluation. This is the schematic of the process structure, having the objective of designing more sustainable energy system with reduced environmental impact. Notice that the core of the procedure is in steps 3, 4, and 5. Similarly to the Exergo-Economic approach, the core step of the analysis is the Exergo-Environmental balance of the components, where the environmental impact costs, BJ, replace the economic costs for flows, mass, for example, mass and heat. Additionally, there are the construction, operation, and the commissioning impact costs that replace the capital and O&M costs of the Exergo-Economic analysis. Here, the units of the general balance are impact points per unit time, PTS, per second generally. This is a relatively simple example of application of Exergo-Environmental analysis to a geothermal resource feeding in series a CHP made of a cogenerative binary ORC and a district heating heat exchanger. The Exergo-Environmental impact of useful Exergy products, power, and the two sources of district heating are expressed here, following the previously introduced balances. As for the Exergo-Economic analysis, two very important parameters to Exergo-Environmental analysis are the relative product fuel increment of impact cost, RBK, and the Exergo-Environmental factor of the component key, FBK. This is useful. They are useful in the evaluation of Exergo-Environmental analysis results, consisting of three fundamental steps. First, identification of the environmentally relevant system components, those with larger B tot. Second, selection of the ones having the highest improvement potential, those with larger RBK. Third, assessment of trade-off between YK and BDK. In components with larger FBK, component-related impact dominates the overall impact. In components with lower FBK, thermodynamic inefficiencies are the dominant source of environmental impact. So this was the last slide, and I thank you for your attention, and I leave the floor to Lorenzo with the case studies. Thank you. I take off my presentation.
No, it's to Claudio.
Oh, Claudio, sorry.
Okay.
Yes, we're not done yet with the methodology. So one more talk, and we're going to give the floor to Claudio Zuffi to give us an insight on the Exergo-Environmental analysis, LCA, data validation and processing, and also the Exergy propagation of environmental costs. So Claudio, sorry, the floor is yours.
Okay. Do you see it?
Yes.
Okay. Good afternoon to everyone. I'm Claudio Zuffi, and now I will introduce the life cycle assessment of geothermal energy and its application to Exergo-Environmental analysis. Life cycle assessment is the best technique to assess environmental impact associated with all the stage of product's life, starting from raw materials up to disposal or recycling. The term product means both object but also energy flows. As in our case, we will use life cycle assessment to evaluate the environmental impacts of geothermal power plants that producing electricity and or heat. This method is organized in 4 steps, and now we are going to see them to understand how to realize LCA model with the goal and scope of evaluating the main environmental impacts of geothermal plants and to finally carry out an Exergo-Environmental analysis. In order to structure a functional way for our aim, the inventory will be organized into several processes. In particular, for Exergo-Environmental analysis, we must pay attention to the difference of subsurface process and surface process, because subsurface process creates fuel cost, and in geothermal case, they are process referred to wells, while surface process create component cost, and they are construction, operation, maintenance, and end of life. When completing life cycle inventory, we have to keep in mind that environmental impact results from direct and indirect emission. Direct emission includes principally the gas carried in the geothermal fluid in a dissolved form and the air pollutants related to the diesel combustions. The indirect emission are associated with materials manufacturing and the energy production required during the whole life cycle of the geothermal plant. it is very important to pay attention on the flows that you are going to model, because each substance, in particular for direct emission, can evaluated in different ways according to the impact method that will be chosen. In fact, every method can express the results in a different ways, because different calculation model and relative assumption are used. And this is reflected on the characterization factor of each flows. There are some critical points for this type of calculation that may related to toxicity issue and the calculation model for hydrogen sulfide. So it becomes necessary to make a comparison at midpoint level in order to choose one of these. In order to make a comparison that makes sense, you must identify categories that are common or similar. Moreover, depending on the method used, one or more sets of normalization and weighting corresponds, which do not always give emphasis to the environmental damage relevant to a geothermal plant. For this reason, GEOENVI project proposed the most damaging impact to be taken into account for geothermal plants, and then classify the impact categories on 3 levels of priority. So, for example, we compare the Elishidi power plant at a midpoint level with the 2 different methods. In this case, the normalization is used to understand how relevant some categories are compared to others. So you can see the difference between this method and the type of results that are obtained. ELCD give the biggest contribution to high priority than RECIPE. And you can see that impactful categories for ELCD are climate change, freshwater ecotoxicity, and human toxicity. While for RECIPE, the impactful categories are the all categories referred to toxicity and water's consumption. When you have choose the method, you can compare your system with other system. In GEOENVI project, it was decided to apply environmental footprint 2.0 to several geothermal plants and compare them. Also here, the normalization was made to understand which were the most relevant categories, and it was deduced that internal distribution in percentage of impact relevance is very different among different technologies. So we have talked about normalization to find out what are the most impactful categories of the system. It must be remembered that both normalization and weighting are not mandatory steps for ISO 14040 and 14044. However, it is a necessary step in carrying out an Exergo-Environmental analysis. It is important to understand that some methods allow the midpoint level to perform normalization and weighting, and then obtain the single score, as ELCD and environmental footprint. Other methods, such as RECIPE, must obtain the results at a midpoint level, then pass at the endpoint level, and then you can normalize and weight to obtain the single score. Usually, it is calculated single score of the whole system, but with this you can make only a comparison with the other system. So the message that needs to be understood is that in order to obtain an Exergo-Environmental analysis, it is necessary to obtain the single score of each component and the single score of all the processes that concern the plant. And now I want to show you this fact. Here you can use the single score of the whole power plant in order to make a comparison, like this example. In fact, there is a comparison with different geothermal technologies compared to other energy production system, like wind or photovoltaic or the national energy mix. Here you can also see how the single score is reduced if improvement to the system are proposed, for the example of Bagnore. But in order to perform an Exergo-environmental analysis, you must proceed in a different way. First of all, we start from thermodynamic modeling and detailed Exergy analysis. So you must identify the relevant component from the thermodynamic point of view. Then we have two cases. The first one, when specific data are available at component level, we go directly to LCA modeling, calculating component single score that represent the environmental cost and applying it to the cost balance. Unfortunately, in many cases, it happened that no specific data are available. In this way, we can model the life cycle inventory using proxies, for example, those developed within GeoEnvy or RINA. Or in common situation is also when data regarding power plant components and they are aggregated. So we have only a total materials amount. What we do is systematically to disaggregate the data inventory following proportionally rules based on component sites from similar plants for which we have detailed life cycle inventories. Then once the inventories has been disaggregated, we will calculate the single score of all the plant component and process, paying attention to proper division of surface and subsurface equipment or related emission. All subsurface component that they are the brown elements are attributed to the input of the system, so represent the fuel cost of the power plant. Then it is important to group all the single score of other components that are present in power plant, but are not so relevant from the thermodynamic point of view. In other words, they are not in the list of the equipment like pipelines or building, and then reallocate their single score to all thermodynamically relevant components on the basis of their Exergy extraction. In this way, we somehow penalize the component with the highest irreversibility. The recommendation are that the system should be disaggregated at finest level, and the LCA should be performed for each plant component or process. Then it is recommended to compare different life cycle impact assessment methodologies applied on the same life cycle inventories. And the normalization and weighting are necessary to build a single score value, which is needed for the Exergo-environmental analysis. And finally, the Exergy approach allows to handle correctly different products like electricity, heat, or cold. So thank you for the attention.
Thank you very much, Claudio. And thank you all for this first session around the Exergy methodology. So now we will be opening basically the Q&A session for guests who might have some questions to our speakers today. So please drop your questions and comments in the chat box, and then the speakers will answer them live. Thank you. So yeah, until then, we can already start discussing a little bit. It was very insightful. I certainly learned many things about the Exergy and Exergo-Environmental and economic analysis. And yeah, I have a question regarding the methodology. So there are a lot of pros, and I was actually quite impressed that it includes, the Exergy analysis includes the cold as well in its process. But what are the limitations in general of such method? I mean, it looks comprehensive and it deals with complex systems, like from simple to most complex systems, but what are the challenges that you often like face in the process?
Well, I can try to answer if you wish, but of course we think this is a good approach, even if it needs, and Claudia stressed it, the validation of the life cycle assessment, because in most scientific publications you find the environmental impact is done using quite old life cycle assessment methods like eco indicator, and they are superseded, and there is some uncertainty in the geothermal field, and I can tell you something about that. But we think this is the correct way to improvement, because both from the point of view of economics and of environmental impact, it gives indications about improvement, while quite often when you only run a life cycle analysis, you come to a global result, but actually it's quite difficult to reprocess the analysis in order to understand what was the key issue, apart of understanding that the problem was greenhouse. Maybe you can get that, or the problem was acidification, maybe, but you don't know what are the components you actually have to improve. Of course, you say, if I put something which removes hydrogen sulfide, that will be much better, but this is quite a qualitative, statement, while we believe that the Exergy analysis can provide quantitative directions to the improvement. This is the main advantage, at least for engineers, and of course the environmental evaluation of the geothermal system is not only a matter of engineering. I'm the first one to recognize that there are a lot of matters which should be considered, but basically we try to apply a technological approach, and we believe this for impacts is correct. I don't want to say more at present. I want to leave space for other questions if there are.
If I only may add something, I would say, in other words, that Exergy method is the engineering bridge to economic and environmental impact assessment. It puts in the middle between the two fields the value of Exergy of energy conversion system components, and allows allocating. So understanding who is the main responsible, or who are the main responsible from the engineering point of view of environmental and economic issues. So I finished.
Yeah, we're still waiting for questions. None is coming yet, but yeah, like we know that Exergy is somehow, yeah, this it assesses the quality of energy, but the term quality can also refer to different things between the work, that is being done, to the transport, to the density and other aspects, and it's quite interesting to understand, like, how do you basically choose or combine these different parameters or attributes to give relevant analysis.
Okay, Amel, I will try to answer, but I would also like to take the remark of Martin Rodriguez, who has put a question in the chat line. Yeah. And the answer to your question, you were asking one moment, because I had seen the other one.
Yeah, it's about like the attributes, the quality attributes of energy. So when you want to assess the quality of the energy, what do you choose? Okay. Only one, or do you combine?
So we didn't go into these details in this introductory presentation, but actually in GECO project we have dealt with systems which are typical of geothermal, which include gases inside the geofluid, and indeed there is an effect on the heat transfer irreversibility when you consider, for example, the main heat transfer process, which is taking place for a binary cycle, which was the case, for example, of Castelnuovo. But indeed, I can tell you that in general, when you deal with geothermal systems, you are in a condition where most of the impact you will see from the application cases is coming from the activity of developing the field and mainly drilling the wells. So there is, of course, a space for the plant optimization, but quite often this represents, with the current technology, which is diesel drilling of the wells, for example, typically you have to deal with something which is within 30 and 40% for the optimization section. So a big part of the impact can indeed be reduced applying, as is done in Iceland, for example, with electric drilling of the wells, or with the correct management and estimation. Of course, what we realized is that the plants which are able to run on a limited number of wells are in a better position than those which are necessarily using, because of course the resource is like that, a considerable number of wells for the same power output. So the drilling activity indeed plays a big role in geothermal.
Yeah. And it reflects in the costs. I mean, financially, it's very...
Yes, it's the same, and it is reflected, you are right, also on the economic side.
Yeah.
And as I wanted to answer to Martin Rodriguez, and at the end of the presentation of Lorenzo, you will see it's not a commercial application, it's something we are producing a kind of open access tool to perform the Exergo-Economic and Exergo-Environmental analysis. And we have already started sharing it as a beta version with some university friends, I mean, not in Italy, but in Turkey and so on. We like to have exchange of this type. And for the Exergy analysis, however, we typically use engineering equation solver for our calculations, but of course we can use any kind of process simulators, or you can even develop your own models in MATLAB or Python or other environments which are connecting to thermophysical properties. So it's the Exergy section is indeed quite open, and you can do it as you like. The Exergo-Economic and Exergo-Environmental, if you like, you can have access to our open access tool. So that's a good news, I think. And for the, I see Martin Ganville is asking how to calculate heat exergy. Well, in general, when we work with the geothermal, we prefer to use a process approach, so to calculate exergy directly from enthalpy and entropy. But if you have to use a heat exergy, that may be convenient in situations where you already know the heat, which is available, for example, in many heat recovery applications. For example, from an engine, you definitely know the heat. And you also know the temperature intervals. So from the temperature intervals, you can calculate an average temperature. There are rules for calculating the average temperature, and the recommendation is to use an entropy mean temperature, because this gives the correct results for the Exergy calculation of heat. So it is absolutely possible to calculate, and indeed, for example, for district heating, we can apply that. Of course, we can also take the Exergy of the hot water, it's not a big problem, but it may be convenient to use that approach. I hope I answered.
Thank you, Giampaolo. So if we don't have any further questions, I think we are ready for a break, and we can come back in 10 minutes, basically. So yeah, so we'll see you in 10 minutes. So welcome back, everyone. We will dive now into the second session, and this session will tackle basically the applications of the 3E, giving you a GECO perspective. And for this, I will give the floor to Lorenzo Talluri, who will give us the last presentation, basically, of this webinar, and then we can open another Q&A regarding those.
Okay, thank you very much for the nice presentation. I'm Lorenzo Talluri. I'm still from Sustainable Energy Research Group of University of Florence. And today I'm going to present the application to GECO reference cases. So Hellischeide, Castelnuovo, and Kisildere. Let's start from Hellischeide power plant, the simplified model. Particularly what we did was a thermodynamic Exergy, Exergo-Economic, and Exergo-Environmental studies of this power plant for the GECO. So we divided it in a simplified model comprehending the high pressure section, the low pressure section, which allows the generation of about 300 megawatt of electricity and 130 megawatt of heat. The simplified model comprehends 18 main components, such as turbines, valve, cooling tower, etc. But as we will see later, all of the components will be taken into account when calculating the Exergo-environmental cost. But before going there, we did also the Exergy analysis. The Exergy analysis, which allows to highlight which were the main components which were inefficient. And particularly, we found that the highest Exergy destruction was found in the wellhead main valve. And this is due to the flash process, which is highly irreversible. The second component, or components in this case, which provide a higher Exergy destruction, are the HP turbines, and this is connected to the turbine efficiency. So the two contribution of wellhead valve and HP turbines are basically comprising 60% of the total Exergy destruction of the power plant. So if we need to improve this power plant, we will need to go and modify this kind of components before going to the others. Finally, the total Exergy efficiency of the power plant was found to be of 49.7%. Regarding the Exergo-Economic results, first of all, we calculated the specific investment cost, which was found to be 3,769 euro per kilowatt. And thanks to the Exergo-Economic process, so coupling economic with Exergy analysis, we finally found that in this kind of power plant, which has, again, 300 megawatt of electricity, this cost of electricity, the realized cost of electricity, is of 3.6 cents euro per kilowatt hour, which is found to be in line with the expected values between 3 and 5 as reported in literature. Furthermore, the Exergo-Economic analysis allowed also the estimation of the heat cost, and was found to be of 5.8 times 10 to the minus 5 cent euros per meters cube of hot water. After Exergy and Exergo-Economic analysis, an Exergo-environmental analysis wanted to be conducted. Therefore, a life cycle analysis was required. Regarding life cycle analysis, the inventory was taken and reworked from published papers, and the aim of this analysis was to calculate single scores for each of the components of the power plant. And particularly, we found two sets of components. The main components, the one that were simulated within the thermodynamic environment, in this case is engineering equation solver, and then the common components, such as, for example, end-of-life, maintenance, or emissions, which are not directly linked to a single component, but which their contribution from an environmental point of view is quite high. Therefore, these components were decided to be distributed, these single scores were distributed through an Exergy destruction method. So each of these contributions can be disaggregated and accounted in one of the main components. in each of the main components. And through these methodologies, we finally identified which were the main responsible of the environmental cost and the main responsible of the not well coupling between the Exergy and the capital, let's say, environmental capital cost. Particularly, all of the components, except for the cooling towers, have a higher environmental impact component. And this is due to the high single score. On the other end, the cooling towers have high Exergy extraction and losses, and therefore this part is more relevant. Finally, we found that the environmental cost of electricity is 0.5 cent points per megawatt hour, and most of it is derived by the direct component impact. On the same measure, also the environmental cost of electricity was found, and it was calculated to 1.01 times 10 to the minus 8 cent points per meters cube of hot water. And also in this case, the majority of this contribution was provided by the component's impact. To conclude the Hellishady power plant case, let's resume the findings. So basically, we found the cost of electricity, both of electricity and heat. The electricity was 3.6 cents euros per kilowatt hours, and the heat generated heat of 5.8 times 10 to the minus 5 cent euros per meters cube of hot water. The environmental cost of electricity was found to be 0.5 centipoints per megawatt hour, and the environmental cost of heat was found to be 1.01 times 10 to minus 8 centipoints per megawatt per meters cube of water. The applied method for the LCA, and therefore the single score utilized in the Exergo-Environmental analysis, was ILCD 2011, weighted with single score impact, and was found that the environmental cost of the geothermal wells is the main responsible of the power plant environmental impact. Indeed, for all the case studies that we assess, the most important component from both from economic and environmental point of view are the wells. And let's see this statement also in Castelnuovo power plant. Castelnuovo power plant is a 5 megawatt organic Rankine cycle power plant, which is a total reinjection scheme. So we have got also a compressor train in order to reinject the non-compressible gases within the well. The layout comprises of a regenerated organic Rankine cycle and a three-stage compressor scheme. The Qualtra power plant, which is similar but doubled in size, will have a similar layout and will be treated within WP9 in GECO. From an Exergy and Exergo-Economic point of view, the main components which needs to be focused are the main heat exchangers and the condenser. Indeed, the Exergy extraction in the main heat exchanger is quite high, and also his cost is one of the most relevant, as lightly followed by the turbine. On the overall, the levelized cost of electricity for Castelnuovo is higher from Hellishady, and this is due to the very low power output, which is 5 megawatt against 300 megawatt, and the cost was found to be 7.15 cent euros per kilowatt hour, which is still very, very attractive for geothermal electricity compared to other renewables. From an environmental point of view, on the other hand, we can see what I was saying before, therefore, and that the wells are the main responsible for the impact, or for the environmental impact. And followed by this, we can see that the environmental impact is lower with respect to the Hellishady, because in this case, we do not have any emissions, and all of the emissions are reinjected. And this provides a lower environmental cost of electricity of 0.265 centipoints per megawatt hour, with a highest contribution, again, derived by the wells. To resume what was done for Castelnuovo, we saw that this whole process allows to identify the largest irreversibilities, both from environmental and economic point of view. We found that the cost of Castelnuovo electricity is of 7.15 euros per kilowatt hour, and the environmental cost of electricity generation is of 0.265 centipoints per megawatt hour. In this case, the component which needs to be well designed is the main heat exchangers, which account for 36.5% of the total power cycle machinery equipment impact, while the wells are the main responsible for the economic and environmental impact. Let's talk about the third case study, and this is Kizilder 2 power plant. This is a 3-flash power cycle, which has also an organic cranking cycle as bottoming cycle, and these power plants provide about 80 megawatts of power. This is a very complex power plant, and for this power plant, we just developed the Exergy and the Exergo-Economic analysis, while the LCA and in particular the Exergo-Environmental analysis are currently running, so I'm not showing the results for those. But from the first analysis, so from what we did was that the Exergy and Exergo-Economic analysis found that the main issues can be found in the HP valve and the binary condenser, where the highest Exergy destruction was found, while the levelized cost of electricity was found to be higher than the other power plants due to the complexity of this power plant, and this was found to be 10 euros per kilowatt hour. So for the Kizilder 2, we just calculated this levelized cost of electricity, and we found that as for the Hellischeide power plant, the main irreversibility is found in the main valve, and again is due to the flash project, which is highly irreversible. And finally, I would like to present an opportunity we like to share with other researchers, and that is an application for simple construction of the Exergo-Economic and Exergo-Environmental analysis. Particularly, you can, inside the group, and I want to say thanks to Pietro Ungar, which was the main developer for this tool. But within the group, we developed a tool for the easy implementation of Exergo-Economic and Exergo-Environmental analysis. You can download it for free, and it's still in the beta version, but here is the link. I think the slides will be available after the webinar, so you can directly click on the link and download it. And this was needed because it allows non-experienced users, and in particular students or young researchers, to perform such analysis in a quickly and straightforward way. How it is done? Basically, you have got to provide some inputs, which is the system topology, so which is the power plant, the components, the connection, and their Exergy values. You can copy and paste it from an IS file or a MATLAB or Python or whichever simulation environment you prefer within the Excel. And then you need also to provide, in this case, I assume the component cost, which can be economic cost, so euro, but they can be also points, so environmental cost. And some correlation are already implemented in this app. However, you can, if you have data available for the specific power plant, it's better to utilize those data so that the results obtained are more reliable. After the inputs are given, an automatic generation and solution of the cost matrix is done, and the outputs are the stream cost, the Exergy, losses and destruction, and the spec indicator, as was described before in the previous presentation. And here you can see that there is a very simple user interface, the Excel input file, and then you can see that you can copy and paste for any program. Here is is because we use engineering equation solver, so you can just calculate the Exergy and then copy it within the Excel file. And there is also an error check tool, which is really useful when you do not, in order to check if all the connection that you need to put are in line. So to conclude, this application is capable of solving complex Exergo-Economic and Exergo-Environmental problems, providing reliable tested results. It provides also the spec indices, which allows the identification of the critical components, and the app is available both in Python and MATLAB versions. And another good note is that we have got remote assistance available through Search Group, and in particular from Pietro Ungarchi, which is the developer of this tool. And the issues could be that at present, the topology input is not so good. I mean, it's an Excel file, so you have to take a bit of time to understand it, but it's not something really difficult. And there's not an option of launching the analysis from a script. So there could be an issue for optimization process, but we are working on it. So I really like to thank you, all of you, for listening to this presentation.
Thank you very much, Lorenzo. I think this has been a very insightful presentation, and I really like the app initiative. This is definitely going to be a game changer for many who want to try this and non-experts. So yeah, thank you. So now we will basically open the Q&A session for our guests. So if you have any questions for Lorenzo or the other speakers, please go ahead and drop them in the chat box, and we shall answer them. So yeah. Okay, waiting for the questions to start coming in. What is your basically perspective on, because you presented like all the GECO power plants and what it would look like for them to to apply this 3E method. Does it make a difference, what is the difference between the clean energy context, like geothermal energy production context, and a normal geothermal power plant? Because what we're trying to do in GECO is to implement this carbon capture and storage, so the CarbFix method in a different context, different geological context, but also different power plants context. So what does it look like for a normal power plant and a CCS one?
Okay, if you want, I can try to reply. Otherwise, Professor, please take the word. Basically speaking, there are lots of benefits, because what we can see is, for example, taking Castelnuovo into account, the simulation, there's, apart from emissions, are taken out. And this is a big impact when looking, depending obviously on the site of the geothermal power plant, but could be several issues, for example, for hydrogens with climate change category, but not only, because we have got also hydrogen sulfide, which is really impacting from environmental point of view. So if you remove all of this contribution and reject it, and then basically we do not have the environmental part, we can see from an environmental point of view cost of electricity, which is much reduced. So basically, it seems that the way we are taking is a good, it's right, but I want to give the word to Professor to further comment anything.
I think, Lorenzo, you got a good point. I mean, this type of analysis outlines that closed-loop plants are very advantageous with respect to current technologies, which, especially in situations like Italy, where you have pollutants like H2S or ammonia or mercury, it's a big improvement to consider the complete reinjection of the non-condensable gases. I would also like to add, I don't know if there is time Claudio could show that the matter of treating correctly this type of emissions is still discussed in the life cycle assessment arena. I mean that there is a large uncertainty for heavy metals, which is a problem in all life cycle assessment methods. And of course, mercury is present in many resources, like in Italy, in Monte Amiata. And as for hydrogen sulfide, the problem is that the most recent methods for life cycle assessment, like ILCD or RECIP or environmental footprint, say that it should not be considered as a contribution to acidification, while it goes into impact categories for human health. So this is the reason why we recommend a benchmarking among methods, even if there is a kind of alignment among these methodologies. And I also would like to underline that until just 3 years ago, all life cycle assessment studies published in the geothermal field were considering a complete conversion of hydrogen sulfide into SO2, and so giving a direct contribution to acidification, which is not now considered. And so there is still something under development, and in fact we recommend to perform a kind of sensitivity analysis when there are these types of emissions, because the overall single score can change quite a lot. I hope I didn't go too much into detail, but this I would like to discuss. We will discuss, I think, these things also within GECO with GEORG, because they are actually doing the life cycle analysis, and the approach to treating this type of emissions, especially if you want to build a single score, is not so straightforward, I have to say.
Yeah, it's actually very important and good to know. I'm trying to keep an eye on the time, I think we're going to close the Q&A session for now. And yeah, and I would like to ask you if you have any final statements before we end this webinar. So I'll start with you, Giampaolo. I think maybe you said a bit of it.
I think I spoke too much, so I'd like to not to speak.
Okay.
I wish to thank everybody for listening, and of course the organization. You are so nice, and it's a good opportunity for us, and we like to share these things within GECO and those outside, and so we are very open to cooperation.
Yeah, thank you. Thank you, Giampaolo. Daniele?
Daniele, you are muted.
Yes, yes.
Still muted. Daniele, you are
Maybe
muted.
now,
Okay.
maybe now, okay. So I wish to thank the organization of GECO and your presence, and the opportunity that you gave to our group to show the activity in GECO, and the sharing of our skills and tools, as Lorenzo has shown in the last presentation, with the other consortium members, especially CIRCE, for joining their expertise in LCA with ours in other methodologies like the ones that we have shown. So thank you again, and I run to my exams because I am late 5 minutes. Okay. So thank you again.
Thank you, Daniele. Claudio, do you want to say something?
I want to thank you for the opportunity to share our work with you, and I hope you find our work.
Thank you, Lorenzo.
Okay, so I just follow up what professors and Cloud say. So first, thanks to organizers, and thanks for the very well structured organization, and all GECO partners. And I really look forward to work with all of you. Also because what we discussed today was very brief, and if you want any more details, please write us, call us. We are really eager to work with all of you. And thanks again, and see you next time, hopefully as soon as possible.
Thank you, Lorenzo. Just before everyone leaves, I want to show you a bit the upcoming events that we have. So we will be continuing the webinar series. This is going to be the first, well, this was the first, and we will be announcing the next ones on time. And we are planning the GECO Summer School. So if you haven't heard about it yet, we're planning it sometime in spring, summer 2022. We will announce the program very soon. You can send us your expressions of interest through any of these channels, and we'll be happy to include you. So so I want to thank everyone. Thank you for our speakers and the guests, and hopefully this was a very a good contribution, and you learned from it. So thank you, everyone. Goodbye.
Bye-bye.
Bye-bye. Thank you, everybody, again.
Bye.